not clear or whatever, you can text me. All right. And actually, some of the students actually feedback some of the labs that you guys are facing. Some of you, not all, some of you are actually communicating with me. What's the difficulties that you guys are actually having? Last week it was more on the I/O, the P1 out setting, P1 in setting, and all these kind of things. That's under the lecture of I/O configuration. So since some of you have raised up, maybe I will pick some question to reinforce that area. Now, today's lecture, it's more of an introduction to interrupts and pooling. I believe this is the first time that you guys are actually hearing these terms, interrupt and pooling. So these terms we will explore more and more in depth in the embedded system engineering, your next year course. All right. But in this current semester for microcomputer, I just want you guys to learn as much as possible about this interrupt and pooling. This is basically something I believe is something new, because you haven't studied about this in electrical system or any other units. Hold on. Hold on. So I believe this unit is beneficial for you guys as an introduction, and also to understand more about the system. If you guys are interested in developing anything yourself, this unit is this particular lecture is quite important. But we are not going to go in so deep. All right. I'm going to give you guys some tutorials on this area. If you guys can understand, then I believe it's good. All right. So what we're going to study this week is about pooling and interrupt. We're going to discover actually what is a pooling, what is interrupt. Basically, this week's lecture is about getting inputs or the main program, the main program being interrupted by some program. Is you can imagine it as a function, but function is scheduled. All right. You have a main program, and then you call, and this main program is being stopped for a while to give way to the function. But think of interrupt and pooling, this kind of things as something that is unscheduled. All right. So you, for example, you are running a main program. All right. And in certain events, the main program needs to be interrupted. Let's say, for example, it's a data logging system. Okay. So when there's certain events of this data logging, it no longer process the usual flow, but it will actually go to service the some of the very important matters, like for example, it could be power issues or whatever, that the microcontroller needs to service. All right. Another good example to explain interrupt is interrupt and pooling is by looking at you have your main program running a program, C programming or whatever, but when someone types in the keyboard, okay, that's a source of unscheduled. Okay, unscheduled. All the interrupts are basically unscheduled. Okay. It's not like a function. Function is something that you call. Okay, you already key into the main program that you're going to call. So function call is scheduled, whereas interrupt and pooling are unscheduled. Okay, you do not know when the user will key in something in the keyboard. So your main program needs to be interrupted. Now, the best way of actually learning programming is by doing. A lot of you will be doing, my experience, 5 years teaching this unit, a lot of you will be doing quite well in terms of theory. What is this computer cycle? What is computer cycle? What is what is the register, how many types of register, so on and so forth. A lot of you will be able to answer. These are short questions. These are not application questions. But when it comes to coding, a lot of you will actually do very badly. Okay, so it's good to actually understand whatever that you're doing in the lab rather than just memorizing. Okay, so, yeah, I hope that no one do this memorizing thing. When you try to memorize, means to say that there is an indication that you don't really understand what's going on in the codes. Okay, so my advice for you is to sincerely do the lab. That's why even though you are actually in teams, I hope that you guys can individually do the lab sessions. That will be, if you can understand every single line, means to say that you would have better understanding. All right. So the only way to learn more about embedded system and programming embedded system specifically is by doing. So if I ask you, how do you implement pooling or interrupt? Sometimes you just learn about it in theory, but when you really do it, when you want to develop an application and you really do it, that's where you really have an in-depth understanding of pooling and interrupt. What is the advantage versus the disadvantage of these two concepts? Interrupt service event, how does the mechanism work? If let's say the user suddenly key in the keyboard, what happens in the CPU? Okay, practically what happens in the CPU is more or less what is happening in function call, more or less, but function call is scheduled, whereas interrupt pooling is unscheduled. Then you have this thing called reset. Now today's lecture is more or less you know means you know, you do not know means you need to do revision, because if you get the concept, there's not much calculation or whatever. It's just coding. You know you can do it. You don't know how to do it. You need to flip through the examples and to understand how these two concepts are being used. Okay. Again, something that's very useful when you're designing a system that has interface with humans. Okay. There's no other way to do it except for pooling and interrupt. Interrupts and resets involve hardware and software components. Since their operation is closely related to how CPU operates, a general look at interrupt is given. Okay, so we're going to give you like a template, okay, and we're going to focus on I/O interrupts specifically. Although there are many sorts of interrupt based on this, interrupt based on that, but one of the most common one, it's interrupt based on I/O. You can use your I/O to toggle or set or reset the pin value to either 0 or 1 to initiate an interrupt. Okay, and implementation of interrupt is a topic that we discuss in depth in embedded system engineering. Of course, this is just an introduction, but nevertheless, I want you guys to have a solid understanding of this concept, because you may want to do some projects in the very near future. Okay, you join the IEEE organization, or even take up some of your projects. Okay, so embedded system is very interesting. I hope that is my sincere hope that some of you will actually spend your holidays in the November period. Okay, November, December, develop some of the projects, play with some of the stuff. Okay, like for example, I know many of you will not be using MSP because it's it's hard to get and it's expensive. Okay, but you may want to use Arduino Uno or Arduino Nano or whatever. Do some projects in your holiday time. Okay, your study free time. That's where you have all the free time. You don't have exams or whatever. You can build something. Okay, build a data logger, build a sensor, build a real-time clock or whatever that you want, and then implement some of the stuff that we've learned. Okay, so this concept, interrupt and pooling, something that you can implement also when you're doing all these projects, especially stuff that deals with user. All right, so the user input functions is unscheduled. The CPU does not know when the user will key in stuff or whatever is unscheduled. Okay, So I sincerely hope that you do something in your holiday sessions. Okay, then you'll be able to appreciate these concepts. Buy some stuff to play around with. Arduino now has a very broad range of IoT products. Now this concept will be very important. IoT will be very important. So understanding interrupt and pooling is also very important because it deals with peripherals, right? So play around with this kind of stuff. See what you can develop. Develop that kind of interest. Okay. Uh, if you don't understand it in microcomputer, you will hate it when it comes to embedded system engineering, your next level of this unit. So when you hate it, you will not be able to score. So you need to love what you learn. Okay, you have to develop that kind of love. It doesn't come overnight. Okay, I cannot make you love something. You need to spend some time with equipments and develop something. Develop an IoT garden, develop IoT gas sensor or whatever. Just play around with this kind of stuff in your free time. These materials are not expensive. If you can buy a $1,000 phone, it's good to invest $100 or $200 buying all these kind of equipments. You can learn and you'll be able to appreciate in the future, right? Okay, let me check any text message. Okay, no text message. That's good. Okay, so I hope that you guys will take up my advice. Do something in your holiday. Develop some IoT stuff. All right, it's a very important concept in the near future. You want to get a good job that pays 4,000-5,000 Sing dollars or whatever. You have to prove that you know all these kind of things. All right. So write a blog, do something, join competitions, whatever that you want. Deal with embedded system, I hope. And make sure you're able to develop that kind of love with whatever that you guys are doing in your embedded system engineering. You cannot go through one semester and just understand a few code of lines and call yourself competent. That's not how it works. Okay. All right. CPU is usually a sequential machine. Now that's the problem. The machine is sequential. CPU fetches one instruction at a time. When you have something that's not scheduled, like for example, keyboard input or whatever, that's out of the sequence. Okay. So how do you make a sequential machine service a non-scheduled instruction set? Okay, I repeat again. How do you make a sequential machine service a non-scheduled instruction? Keyboard key in values using a keyboard is not scheduled. Okay, the computer sequentially fetches, decode, execute. This one we know. It's always three states. Okay, that the CPU continue to cycles. In these three states. And we're going to actually study what is the mechanism involved. More or less, it's going to be like function. We know we have that kind of intuition. Okay. Single CPU can only be executing one or two instructions at a time. When it comes to CPU servicing peripheral, these are unscheduled services. All right. Service means is a lingo. Service means I receive input. I need to service some equipments. Let's say, for example, you're doing data logging. Suddenly, there's a temperature rise. You need to send SMS to the mainframe. Sensor AB is currently heating up. You need to stop everything and give a call to the maintenance engineer. So this is an example. How do you know when the sensor temperature will rise? So it's not scheduled, it's not programmed in your main code. That's why it's called unscheduled. Okay. So how do you make a sequential machine perform this task to service an unscheduled instruction? At its basic level, I'll give you a very clear example. If you cannot accept my example of temperature sensor or whatever, you feel it's too complicated, just look at focus on keypad. Okay, at this most basic level, keypad is an array of switches, one per key, where software give meaning to each key. Okay, when you press something, basically it's just an interpretation. The machine interpret. Switches are organized in such a way that it yields a different code. For every keystroke, the CPU needs to retrieve associated key code. Okay, so when you press the G or A, computer need to interpret whatever that you're keying in. Now this keypad is an example of what we try to how we want to visualize the interrupt and pulling. Okay, the action of retrieving the code, each key passing them to a program, is what we call servicing the keypad. Now this is an example of the service. What service? Unscheduled service. All right. CPU continues, interrogates, or pulls the status of the device to determine if service is needed. Okay, so now the CPU, which is a sequential machine, okay, needs to service, needs to look into whatever the user is keying in, and this key in thing is unscheduled. So how do we do it? Okay, the first and the most obvious way of doing it is by using a pooling system. Okay, means to say that the computer keeps on checking the status of the keyboard. Maybe you have a register. When there is a new information, there is a flag that's being flagged up. It could be one of the register. So when the flag is being flagged up, okay, this is where you can use the pooling system. Pooling means you check the register value every computer cycle. Okay, let's say for example, your main. Okay, your main program consists of a lot of stuff. You probably write one line. Okay, if this bit, which is the flag, is on, then you do something. You receive information from the keyboard or whatever. Now this concept is called pooling. All right. So you hard code. Okay. You guys like to use the word hard code. I do not know what defines hard code, but over time, I understand that when you're doing stuff in lab, you guys always use the word hard code. I also learned from you guys. Hard code means you key in. You do not use extensive for loop, if loop, whatever. Okay. So basically, pooling is a version of hard code. Okay. You in every main in the main line. Okay. Maybe your main program consists of 4 or 5 lines, and one of the line will be consist of checking if flag equals to 1. Okay. You do this. You blink an LED or do whatever. You have a pool. Okay. Now this is a pooling system. You can integrate this pooling system with functions, okay, subroutines, function or whatever. Now let's give an example. Pressing the button activates a register bit, okay, and in your main program, okay, you can keep on checking the register bit value. If the register bit value equals to 1, you blink an LED and then you go back, okay, to the main program. Blink for 1 second, then you go back. Okay. Now this kind of example called pooling. And what is a requirement for pooling? You need to have hardware flags. Okay, hardware flags. Okay, let's say for example, there must be 1 bit in the register. Okay, that allows you to check the status. If there's a new information, that flag will change its value, toggle or whatever. All right. Now some of this pooling system involves detecting toggle, detecting a reset, or detecting a set. What do I mean? Okay, so if you want to check the status, sometimes it depends on the sensor or the peripheral. Sometimes they return if there is information, refresh information, the value toggles. So from 0, it will toggle to 1. Sometimes it will be auto reset. In that case, you need to see whether that bit is 1 or 0, set or reset. Okay, vice versa for pins, peripherals that have reset values. Okay, so you need to program your CPU accordingly based on your peripheral, whether this device is a toggle, this device produces a set, or this device produces a reset. Imagine you're expecting a phone call. Your phone's speaker is broken, so you cannot hear the ringers. And let's say that is the screen is broken too. Let's say this is just to help you to visualize what is pulling. Now the only way to make the call is to periodically pick up the phone and to check to see if there's a call. Okay, so you can imagine the phone that you're having right now, the ringer is broken, so there's no way to know when the ring, okay, the ring happens. There's also no way to check the screen because the screen is broken. So what you can do is every 5 minutes listen to your phone manually to see if there is a incoming. Okay, if there is an incoming ringtone tone that you hear, you can press listen. Okay, so you can press the green button to listen. So this is a very typical and good example of understanding pulling. When a peripheral is served by interrupts, okay, now this is the opposite of pulling. Interrupt means it's not hard coded. Okay, you need to use an I/O pin to perform an interrupt. Means to say that it's basically a smarter way of performing unscheduled function calls. Okay, so let's say for example, when a peripheral is served by interrupts, suddenly there's a, just imagine this word for a while before I explain further what is interrupt. Okay, now when it is being served by an interrupt, it sends a signal to the CPU notifying of this need. The CPU is called, the signal is called interrupt request or IRQ. Okay, it can be a pin. It can be a pin that when there is a signal coming, it resets the pin value so that you can actually, the CPU can actually detect, okay, this pin value is reset or set. By that, we know that there is an interrupt request. Okay, so we detect the CPU might be busy performing other tasks, or even in sleep mode. What do we mean by sleep mode? A lot of your devices, for example, your handphone especially, what happens when you're on it 24 hours? Okay, the battery drain very fast. All right, so you might not care so much at this moment. What about power issues? But when you're really in a company developing a product, an IoT product or whatever, now power becomes a very critical optimization problem. You want to make sure that the device that you are developing, it's power efficient. Look at your smartwatch. Okay, when you are not reading or whatever, the smartwatch actually go to sleep. But some of the background functions are actually happening. Like for example, the real-time clock is continuously working, and the all these WhatsApp calls or whatever, they are being suppressed to sleep mode. This is for power consumption. Right? You do not want your phone to dry up or whatever, and because of this, sleep mode needs to be interrupted. Okay, you get up from your sleep mode and then the computer do something. When the interrupt request comes, the CPU suspends the task that is currently running, wakes up from the sleep in the case of sleep mode, executes the specific set of instruction, and then probably you go back to sleep mode, or you go back to the main program. This event is what we call interrupt. Now, in this case, you don't need to check the bit every computation cycle, every main loop. You in the pooling concept, the main program actually checks the flag. Not so with interrupt. Okay, interrupt, you use a IRQ to replace the manual checking. The set of instruction executed to serve the device upon an IRQ is called an interrupt service routine. So what happens when the interrupt is being called? Okay, now let's give an example. If I press a button, okay, out of the blue, okay, I press the button out of the blue, the MSP 430 will need to blink an LED. Now, what is this called? This is called, the blinking of the LED is called interrupt service routine. Okay, this is the routine that needs to be serviced every time there is an interrupt. So we call this interrupt service routine. Which is the interrupt service routine? It is the blinking of the LED, not not the interrupt in the pin. This is called the interrupt in the pin is called interrupt, but the blinking of the LED itself is called interrupt service routine. Now, I'm giving you some definitions, probably in tutorials or whatever. I'll bring up one of the codes and to show you, well, this is what we call the interrupt. Which part is called interrupt service routine? Now, how do I modify the codes such that the LED will blink for 1 second, 2 seconds, so on and so forth? How do I make the LED blink faster? These kind of questions are very common in interrupt related questions. So I need you guys to actually look into this. I might find some external codes or whatever to actually discuss which part is interrupt service routine, how do you use it, okay? Now imagine if you have, back to our phone example, working phone and you're either asleep or in the middle of playing a video game. As soon as you hear the ring, you interrupt your game and wake up and answers the call. So basically, pulling is no screen, no ring. But interrupt is you have a ringer. Okay, so you can do your tasks, you can hang around, play video games or whatever. Whenever there's a ring, you stop whatever that you're doing, and then you service. Okay, you answer your boss, you attend to some emergency cases or whatsoever. So that is what we call attending to the emergency service is called an interrupt service routine. Okay, whereas the action of listening to the ring is called interrupt request queue. All right, IRQ. An example of interrupt in embedded system, a system that turns on an LED when a change in pressure is sensed through a sensor. In this case, we could have the CPU in a loop or in a low power mode. Again, something that you ask yourself, hey, what is this? Whenever you're designing a sensor, low power mode becomes very important. Okay, so that's why I like you guys to take November and December, do some projects. I'll be happy to entertain you if you are using Arduino. The rest of the products, I'm not familiar, but if you're doing something with Arduino, either ESP8266 or whatever, you guys can just give me a call or email. I'll be happy to entertain you guys, even though it's not within this unit, because it will be very important. It's a value added to your CV, your skill set. You cannot learn microcomputer or embedded system simply by listening to lectures alone. So you need to do something. In fact, if you keep on doing stuff, you'll be more proficient as compared to just by listening to the lectures. The ISR could trigger the code that turns the LED on. Okay, so the interrupt service routine. Okay, where is the routine? The routine could be blinking an LED for 5 seconds. So you look at the code, change the code in such a way that instead of blinking this LED, it blinks another LED, or it blinks the LED 3 times and then go back to the main program. Now, how are you able to do this? Can you do this or you cannot do this? Cannot. Theoretically, you do not understand interrupt fully. The advantage is, this is another very popular question. Why do we want to use interrupt as compared to pulling? Okay, in many cases, it is preferred to use interrupt, especially when combined with a low power mode. You imagine in a pulling, you need to keep cycling and understanding. Hey, is the device being called, the peripheral being called, or etc. etc. Now, which would you prefer? When you're playing game, will you prefer checking the phone every 5 seconds or wait for the ring to come, then only you check your phone? Definitely, it's waiting for the ring, then you check the phone. Okay, so this is the main advantage of the interrupt. The main program does not have so much computational load. Okay, using interrupt can lead to less power consumption, and implementation usually does not require as many computer cycle. Imagine you have 6 lines and you have one if else loop to implement the pooling system. Okay, So irregardless of whether someone is calling or whatever, you will need to actually check the phone. So that's very tiring for the CPU. The CPU needs to do more stuff. Okay. So when the CPU is loaded, you do not have so much leeway for your memory. Okay. But that's in the case of really optimized codes. Interrupt-driven system may be susceptible to false triggering. Okay, this is very true. When you have interrupt, of course you have problem. When you have every single engineering is a trade-off. All right. Whether you have when you have an interrupt, advantage is power consumption. Disadvantage is susceptible to false trigger. Okay. Now why is susceptible to false trigger? Because say that for example triggering by a pin. Okay, you're triggering anything that it's more than 5 volts. You service the routine. You blink the LED. But in the case where the voltage is probably due to a power source noise or a spike, how would you actually do it? So this is a problem. It's very susceptible to noise. So if you have a noisy environment, pulling this interrupt might not be so popular solution. If not handled properly, interrupt system may have delayed process response to different IRQs. Okay, so that for example, you have 5 pins that enable interrupt. Arduino Uno, you have 2. You have pin 2 and you have pin 3. If you enable it, you have pin 2 and pin 3. Arduino Mega have about 4 or 5 interrupts. Again, it depends on what type of embedded system that you're using. Okay. A type of interrupt request queue that can be masked or disabled by cleaning the CPU's global interrupt enable GEIE flag in the processor status PSW. Now, reflect back status register. What do you have inside? Okay, we know that the upper byte is basically empty. All right, it's a lot of hidden stuff that are not important for us. What about the lower byte? Okay, the lower byte contains GIE. Look into your textbook. Where is the GIE? Okay, it's either 1 or 0. When you put it into 0, all these maskable interrupts will not be functional. Let's say, for example, you have a pin. Okay, and when this pin receives 5 volts, it goes into the interrupt routine. But sometimes because of power instability, you have a lot of interrupt requests that are actually not valid interrupt requests. They are just because of power issues. They are noisy. The DC is noisy. There is intermittency. All right. In this case, it's better to disable all the interrupt. Say that, for example, I'm not using any interrupts, so I can disable it. Okay, by pushing the GIE into 0. GIE is inside the status register. Please go and find out which pin. All right, which byte is it? Byte 7, byte 6, byte 8, bit 7, bit 6, or so on and so forth. This gives the programmer ability to on deciding when the CPU would respond to IRQs. These interrupts are the most common used in embedded system and are just usually referred to as interrupts. They are maskable. You can mask it, means to say that even if the interrupt happen, it will not proceed into a valid ISR if you disable it, the GIE. But what about those non-maskable interrupt? Now it's very important. Why must we have interrupts that cannot be masked? Okay, a lot of reason. Power, brownout, power issues. You're plugging in a 12 volt into the embedded system. Suddenly there is a dip. Okay, it can actually spoil the embedded system, but there is a dip from 12 volts. Suddenly you have until 2 volts. What can be done? Okay, nothing. These are interrupts that are necessary, should not be masked by the programmer. It should be a hardware-based mask. Okay, it can be disabled by clearing GIE, but not always. Even these non-maskable interrupts, there is a way to actually disable it. There is a way, but this is for more advanced stage students. All right. If I can dig out some stuff during tutorial, I'll let you guys know. But if you learn about this at this moment, then what are you going to do in your embedded system? So I'll see what are interesting stuff that I can actually bring up for this particular subject, maskable and non-maskable. Different CPU architecture might have different ways of servicing IRQs. Yes, that's true. A lot of ways of doing it. Again, there's a lot of you want to do something. Arduino, sensors, all these kind of things. Once you start doing stuff, you'll be able to learn it. You'll be able to create philosophies. What must you do? What mustn't you do? And all these kind of things. These differences can be seen in the way of handling pausing currently. So there's a lot of way to actually do interrupts. In general, the following 6 steps are taken to service an interrupt. Now, these are just guidelines. Okay, we're going to take the MSP 430 as an example. Now, step 1, finish the instruction being executed. Whenever you call, the instructions that are currently being serviced by the main program will be executed. It will be finished first before it goes into another line of interrupt service routine. The CPU never truncates instruction, which means that IRQ are served between instructions. Okay. The next step will be you complete whatever tasks that are already being serviced by this CPU. Once the task is completed, then you have the interrupt service routine. Save the current program counter value and the status register. Why status register? What if we don't save status register? Okay, if you do not save status register, once you go back into the main program, all your calculations will be gone. Remember what's in the status register? We have flags. Okay, we have arithmetic flags, carry, 0, whatever. So if this status is not being saved into the stack pointer, what will happen is once you go back to the main program, everything will be jumbled up. It doesn't make sense anymore. So it's imperative that the status register is actually being saved. Okay, some processors might save other registers as well. It depends. Okay, but generally the PC value, the program counter value, and the status registers are the most important stuff. You might have other stuff, other brands might implement it differently. So this is a topic for chip design. All right, it's a very advanced topic. If you guys want to study it on your own during holidays, you can go ahead. Can I design a microcontroller that it's far better than what it has in the market? Well, if you have an idea, you want to have more stuff that being pushed on the stack apart from PC and SR, you can do so. Design your own microcontroller. Step 3 involves clearing the GIE. Okay, you clear this action disables. Now, your interrupt can only happen one interrupt request at a time. So when you are servicing one interrupt, the other one will have to be queued or will have to be waiting. So in this short period where the interrupt request, the interrupt ISR is being executed, in this very short time, probably point something microseconds, in this short time, the GIE is temporarily disabled. Why disabled? Because it does not want a new interrupt to come and disrupt the existing interrupt. Okay, again, why is it being cleared? Because it does not want the existing interrupt request to be interrupted by another interrupt. Okay, so that's why the CPU is designed in such a way that the GIE will be temporarily disabled. Okay, this action disables interrupting and ISR under the execution. So you do not want to interrupt an interrupt request that is currently going on. Only one can be processed at the same time. So when you are servicing an interrupt, what happens is everything will be temporarily frozen. No requests coming in until that particular instruction, the ISR is being completed. Then the CPU will enable back the interrupt flag. Okay. Step 4. Now, once you disable the GIE, of course, you will load the PC with address of ISR to be executed. The blinking, for example, the blinking of the LED. Okay. So once the main program stops for a while, the LED will be blink. Okay. And then after that, it might load back the original address for the main program. Okay, so the main program is probably doing something at the moment. It's probably in sleep mode or doing something, and when you interrupt it, it needs to go back to the state before the interrupt is being executed. Okay. The result is always the same, which is to put address first instruction of the ISR to the PC. So now at step 4, ISR is being executed. Okay, in your case, in your laboratory, most probably it will involve a LED. You execute step 5 is the easiest. Execute. Okay, so a question might ask you, hey, what are the 6 steps to enable ISR? Okay, so these are the 6 steps that you answer. It could be a short essay or whatever. So this is how you answer. The interrupt service routine ends with special instruction set return. Okay, so basic return, you have of course this is in the case of assembly language. You have your return return or RETI, return to instruction. And the final one is how do you go back to the state before the interrupt is being requested. So you get back whatever that you have loaded onto the stack. Let's say, for example, the PC value and the carry bit, negative bit, whatever bit that you have previously saved in the stack register. Take it out, put it back to where it belongs. All right. So it's actually restoring the state of the computer before the interrupt is being called. Now, fundamentally, there are 4 basic requirements. In order for your CPU or your embedded system to be able to do interrupt, you need to have 4 features. Your CPU needs to have 4 features, okay? Your CPU needs to be able to save the PC or the SR. Maybe you come up with a new design of microcontroller that does not need stack. Fine, anything. Okay, you can have anything to replace. You can have a dedicated register if you want. Generally, they use stack register. Okay. Generally, the first requirement is you need some way of saving the PC and the SR. That's the most minimum. You can save other stuff as well. Doesn't matter. Second requirement is having an ISR designed to render service needed by the service interrupt request. So you have to have an ISR. Your embedded system have to have a ISR attached to the main code. What happens in your ISR? Blink an LED. What happens in ISR? Do this, do this, do this. So you have to have a ISR designed to render the service needed by the device. Could be as simple as blinking an LED. All right. The third requirement is means for CPU to locate the ISR corresponding to the request. Okay. If pin number 2 is being toggled, what type of ISR is being called, etc., etc. So you need to define it in your main code, in your coding. So please go back and study this part in the book. Okay, you can go and check ISR, the ebook that I gave you. Study the example of blinking LED using an interrupt. That's very clear. That part is very clear. Okay, questions might twist and turn, ask you modify this, modify why the code does not work. Now this is a very common question. All right. So the CPU have to locate the ISR corresponding to the IRQ. If you define pin 2 as an interrupt for this, no, do this. I have a project one time that uses interrupt, and because it's not very stable, I decide to use actually pooling. I generally find that for Arduino, using interrupt somehow has a bit of problem. Probably I have power issues or something like that. So if you're doing some project, if is the interrupt is not very stable, go back into pooling. Pooling concept is normally more stable, but power consumption is slightly higher. Okay. Now the fourth requirement enables you need to be enabling the interrupt in the system. If you don't enable it, the GIE or whatever, you cannot be using a GIE. In our case, CPU MSP430 is the case of setting the GIE. Okay. Okay, setting the GIE. So if your GIE is 0, you set it to 1 to enable the interrupt. So that is the 4 requirements. Probably 6 steps, 4 requirements. You can go back and study. Okay, if you understand interrupt, then it's good. Okay, take this example. If you can see this part here, okay, these are timer settings. You don't have to go so far. Basically, these are just timer settings. Okay, now understand this. What does it mean? That means port 3, the 7-bit is being set, so you don't disturb the other bits. Port 3 is being set, and port 3 direction, the 7-bit, the 7 pin is being converted into an output pin, and this value of the output pin has become 1. So if you connect an LED to this pin, what will happen is pin number 7 connected to the LED will light up. Okay. Now this is an this is a function. This is a while function. This is a main program. Okay, this is a main program. You loop it forever. Okay. So the reason this one is basically to enter the low power mode. The command is given low power mode. And what is this? This is associating timer A with this interrupt service. You can use a timer also to call the interrupt service. So whenever this timer is associating this timer with this interrupt, so when it is actually interrupted, probably using one of the IO pins, I don't know, this timer is interrupted. I think, if I'm not mistaken, there is a specific pin, okay, that is designed to carry out this ISR. Now, when this ISR is being carried out, is probably a toggle or whatever. It is a scheduled interrupt. Okay. And when this is executed, what is the ISR? What is the action that can be achieved using the ISR routine? So this part, the low power mode is temporarily off. Okay, that's all. It doesn't even blink an LED. Does it say any blinking of the LED? No. Okay, so you can use a timer to interrupt. You can use a timer to perform an interrupt. In this case, one of the pins will be associated with the timer. Whenever the timer counts to a certain count, this one will be executed. So you will see that once in a while, following this cycle, the low power mode will be turned off. Okay, so you can see most of the time it will turn on. Sometime it will turn off. All right, so this is an example of not by using a pin to initiate an interrupt, but by using a timer. Okay, probably next class we will check out timer, but suffice to just go through with you guys. So this part is for the setting the low power mode. When the timer is counting to a certain number, the low power mode will be off for a while, and then it goes back. Okay, so whatever that we learn, pushing the stuff to the stack pointer or whatever, this is where you can actually apply. All right. Okay, so we understand about pulling. You can write your own codes. I'm very sure that some of these lab sessions you will have interrupt and pulling. Is this an introduction? Now we go into something that's more clear-cut, a reset. Okay, so what is reset? Reset is something that Watchdog, for example, is a type of reset. Reset is an asynchronous signal that when fed to an embedded system causes the SP and the most sequential peripherals to start from an unknown predefined state. Okay, remember what we talked about, the 3 computational states: fetch, decode, execute. Fetch, decode, execute never stops. It keeps on going as long as there is power applied to this embedded system. Now, what happened is sometimes in certain circumstances, you need to go to the reset address. Go and look for that particular picture in my lecture slides, where there is a reset and then it goes into the three computational modes: fetch, decode, execute, fetch, decode. But it always starts with one reset address. Okay, no matter what you program, it will always start from that reset address. So this state is specified by the users based on your datasheet. Where is the reset address? MSP, where is it? Arduino, where is it? Etc. etc. Now, what causes the address or the reset to be executed? Sometimes while it's running, it will automatically go to the reset address. Why must it go to the reset address? Now, these are the few situations where you need to go to the reset address. Power on rest. Suddenly, you need to reset. You manually press reset. Arduino, there's one. I think it's pin number 1. Okay, once you press it, you ground it, it will go to power reset. Brown out means to say that there is insufficient voltage level. Suddenly 5 volt will drop to 1.5, so on and so forth. Okay, brown out, okay, is another example, okay, of power supply. Sometimes there's a dip. Maybe you buy the power supply, it's not so clean. So there is a dip, and then because of this power dip, it will go into reset address. The reset may also be generated by hardware event, like for example the watchdog timer. Okay, so how do you detect that your computer is hang? Look at the watchdog timer. Reset can be viewed as a special kind of interrupt. Oh yes, okay. So the ISR is the action that you take instead of the LED is to move the PC to the reset address. So it's a very special kind of interrupt. Means to say that instead of blinking in LED or low power mode, it brings the CPU to the address, the reset address. Upon reset, the PC is loaded with the address of the first instruction to be executed. Then, after that, you go into your fetch, decode, execute cycle. Okay, so I think that's all for this week. I'll try to bring up some examples, particularly reset. Okay, so the requirement for this lecture, I just want you guys to be able to understand, state it clearly what is reset. Okay, and probably to understand the codes. The question might ask you, what does this code do? Why this code doesn't work? Okay, probably something in the instruction set. This is a template. All right, you look at this. All right, look at this, and we're not going so deep into this, but the template probably looks like this. You have your main code, so do something, main code, and then you will define your interrupt. Okay, so this vector, pragma vector, it defines what triggers the ISR. Is it a IO or is it a timer? In this case, it's a timer. So the question most probably will ask you something like this. I will give you some examples. Why this code does not work? What does it do? In this case, you will have to understand this pattern of code using interrupt. You don't understand, this is a very long question. Normally, it's a very long question. If the format doesn't change, but you see change, question might change. Okay. Okay, so that's all. Beware of these questions that are related to the code. I suggest you understand interrupt, pooling, and reset. This is a very simple concept. You get it, you get it. Okay, if you don't get it, send me a text or whatever. Try to explain further to you. Okay, so that's all for today. I see you guys again for the tutorial sessions and the any questions in the lab. I hope that you guys can complete it as soon as possible. We'll go to revision very soon. Okay, see you guys.